Welcome. Imagine you are in a crowded school cafeteria and one person walks in with a highly contagious cold. If they sneeze, who gets sick? It is not a guaranteed outcome. It depends on who is standing nearby, which way the wind is blowing, and pure chance. Today, we are diving into stochastic epidemic models, a fascinating area of biostatistics that uses probability to predict how diseases spread in the real, unpredictable world. Now that we have pictured that cafeteria sneeze, let us understand the math behind it. In a deterministic model, we assume a disease spreads at a perfectly smooth, continuous rate, much like water flowing from a tap. But real life is messy and unpredictable. A stochastic model treats every single interaction as a random event, like flipping a coin to see if someone catches the bug. Instead of predicting exactly 50 people will get sick tomorrow, these models tell us the probability that 50 people will get sick. This randomness is crucial when an outbreak first starts. To make sense of this random spread, scientists rely on the SIR model. This model divides the population into three distinct groups. Susceptible refers to healthy people who can still catch the disease because they have no immunity. Infected refers to people who currently have the disease and can spread it to others. Finally, recovered refers to people who have beaten the disease and are now immune. In our stochastic framework, moving from one group to the next is not automatic. It is driven entirely by probabilities and chance encounters. So, what controls how fast people move between these three groups? We define two main parameters. The infection rate, denoted by the Greek letter beta, is the probability that a contact between a susceptible and an infected person results in a new infection. The recovery rate, denoted by gamma, tells us how quickly infected people get better. Gamma is actually the reciprocal of the average time a person remains infectious. These two rates act as the engine driving the epidemic forward or slowing it down. These two rates lead us to the most famous number in all of epidemiology, the basic reproduction number or R0. Conceptually, it compares how fast the disease spreads to how fast people recover. R0 is the expected number of secondary cases produced by a single infected person in a completely vulnerable population. If beta increases, R0 goes up, meaning the disease is more contagious. If gamma increases, people recover faster, giving them less time to infect others, so R0 goes down. If R0 is greater than 1, an epidemic occurs. Let us see this formula in action with a concrete example. Suppose a new strain of flu appears in a small town. Health officials observe an infection rate of 0.4 people per day and the average infectious period is 5 days. We need to find the recovery rate and R0. First, we find the recovery rate gamma by taking the reciprocal of the infectious period. 1 divided by 5 gives us 0.2. This means 20% of sick people recover every single day. Continuing with our calculation, we now substitute our values into the R0 formula. We divide the infection rate of 0.4 by our recovery rate of 0.2. This gives us exactly 2.0. What does this mean physically? On average, every sick person will infect 2 other people. Because 2.0 is strictly greater than 1, the disease will spread exponentially and an epidemic will occur unless interventions like vaccines or lockdowns are introduced. Now that we know how to predict if an epidemic will grow, let us look at the very beginning of an outbreak. When a disease first appears, there are very few infected people and a massive susceptible population. Because the susceptible pool is so huge, we can temporarily ignore the fact that it is shrinking. We treat the spread like a family tree, where one infection branches into new ones. This is called a branching process approximation, and it helps us calculate the exact probability that the disease lineage will completely die out purely by luck. To better understand this, let us look at a visual representation. At the top, you see the SIR model boxes, showing how individuals transition from susceptible to infected to recovered, governed by the rates beta and gamma. Below that, you see the branching process in action. The red dot at the top is the very first infected person, branching out to infect two others, just like a family tree. This diagram perfectly captures how a single random event can multiply over generations, which is exactly what our approximation calculates. This branching visual brings us to the fundamental equation for extinction probability. Here, P represents the total probability that the disease completely dies out. P of 0 is the chance of infecting no one, and P of 2 is the chance of infecting exactly 2 people. Notice that we multiply P of 2 by P squared. We square it because if 2 people are infective, both of their subsequent transmission chains must independently die out for the whole disease to go extinct. We can set up this equation and solve for P. Let us apply this equation to a highly simplified stochastic scenario. Suppose an infected person enters a completely susceptible population. Due to random chance, they will infect 0 people with a probability of 0.6 or 2 people with a probability of 0.4. We substitute these given probabilities into our extinction equation. To solve for P, we rearrange the equation by moving all terms to one side, giving us a standard quadratic form equal to 0. This allows us to use basic algebra. Continuing from our quadratic equation, we apply the standard quadratic formula to find the roots. We plug in our coefficients. A is 0.4, B is -1, and C is 0.6. We carefully simplify the terms inside the square root, which gives us 1 minus 0.96. This leaves us with the square root of 0.04, which simplifies cleanly to 0.2. We now have a simple fraction to evaluate by adding and subtracting. Now we solve the plus and minus options to find our final answer. Adding gives us 1.5 and subtracting gives us 1.0. However, a probability can never be greater than 1. Therefore, the only valid physical answer is that P equals 1.0. What does this mean physically? It means that despite the chance of infecting 2 people, the disease is absolutely guaranteed to eventually die out on its own in this specific stochastic model. Having seen the math, we must ask why this matters in the real world. Stochastic epidemic models are the absolute backbone of modern public health policy. While deterministic models might predict a massive wave of infections, stochastic models tell us the actual probability of that wave happening. They help us understand how random events like super spreader gatherings can ignite an outbreak. Without these models, governments would be flying blind, unable to account for the natural randomness of human behavior when deciding how many vaccines to manufacture or when to close schools. We have covered a lot of ground today, so let us review the most important ideas. First, stochastic models embrace the randomness of real life, unlike deterministic models. Second, the SIR model helps us track the flow of a disease, and the basic reproduction number tells us if an outbreak will grow into an epidemic. Finally, using the branching process approximation, we can calculate the exact probability that a new disease will die out before causing a pandemic. You now have a solid understanding of how probability predicts pandemics.